Welcome to another episode of Well, Don't Tell the Kids. I'm Janet Lee, your host, and today my guest is Dr. Joshua Gold. Welcome to the podcast, Josh.
Well, good morning, Janet. Thanks for having me.
Josh joins us from a suburb of Philadelphia, where he is a professor of neuroscience at the Perelman School of Medicine at the University of Pennsylvania. Now, Josh and his lovely wife, Cecilia, are busy raising their family in the suburbs of Philly. Are they keeping you all busy?
They're keeping us very busy. They're having a very good time this summer, swimming and reading and doing kids stuff.
Excellent. But you're originally from a suburb of Washington, D.C.
That's right.
Yep.
McLean, Virginia, of course.
All roads go through McLean.
That's right.
And you studied neurosciences at Brown. What got you interested in this field to begin with? Was this something on your radar as a high school student, or how did that come to be?
Yeah, not particularly as a high school student. Back in the day, it was not something that was taught very much in high school. These days, I'm happy to say it's a little bit more common. No, you'll be happy to hear that the answer to your question is the answer to most questions, which is my big sister is what did it. My sister preceded me to Brown, and when she was a freshman there, took a course, Introduction to Neuroscience, that she really enjoyed and suggested that I try it when I arrived there. And it was a great course, and that's really what got me interested.
And then you worked your way through that and eventually got over to the left coast and studied at Stanford University, earning your doctorate in neurosciences there. Can you tell us a little bit about the doctoral research that you did there?
Sure. Yeah, it was a fun time. The lab that I worked in with Professor Eric Knudsen, a longtime faculty there, actually studies barn owls.
Barn owls.
Barn owls. Yes, you and your listeners probably would recognize them even if you didn't know them by name. They're the owls with the white pin feathers on their face in sort of a heart shape. And it turns out that these owls are exceptionally good at hunting for their prey at night. And so they are able to find little critters scurrying around, barns, very well just by figuring out where they are based on the sounds that they're making. And this ability to, so-called sound localization ability, to locate the source of a sound is something that is learned. It's not, part of it is innate, but part of it has to be learned, and it has to be learned for a very actually straightforward reason. That one of the ways in which barn owls and humans and other creatures are able to localize sounds is by comparing very small differences in timing of the sound reaching one ear versus the other. So when someone is speaking and is standing to your left, their sound reaches your left ear before it reaches your right ear. And so when you close your eyes, you're able to tell that they're standing to your left, in part because the sound comes to the left ear sooner. It also is louder in the left ear as well, and that's another cue. And so let's get back to learning. So I said learning was that this ability is learned. And why is it that? For a very simple reason. The timing difference between the two ears depends on the distance between the two ears, and that distance changes as you grow. So as you grow up, your head gets bigger, and so the actual cue that your brain has to use to determine this sound localization cue, this ability to compute the difference in timing between a sound reaching your right and your left ear, changes over time. And so your brain has to learn how to interpret that correctly. And so we were studying how your brain does that learning. What is the actual changes in your brain that allows them to learn to compute that as you grow up?
I see.
Well, as the barn owls grow up.
Oh, yes. Well, so the owl's head is quite a bit more mobile than ours, right? And
that's right. And so part of that is their ability to sort of sample space as they look around and move their head around to listen for different cues. But their ability to localize sounds is they're exceptionally good at it. And one of the ways that is really interesting about that is that their heads not only swivel around, but obviously their heads are much smaller than ours. And so the timing differences that they hear are much smaller than the ones that we hear. So it's actually a much harder computation for them, but their brains have managed to solve it in a way that's about as good as ours.
I wonder, dangerous thing when I start to wonder, I wonder if a larger percentage of the owl brain is dedicated towards that task than, say, ours. Dedicated.
Yeah, no, those are very good instincts and good question. That probably is true. We still don't really understand all the parts of the owl's brain that is dedicated to this kind of computation, nor do we really understand all the parts of our brain that's dedicated to vision, as you say. But roughly speaking, what you say does seem to be exactly true, that we are very visual creatures, and that is reflected in the fact that very large portions of our brain involve visual processing, and similarly for owls and their processing of audition. And so, real estate matters, not only in the real world, but in the brain. And having more real estate in the brain to process a certain kind of information is usually a pretty good indication that information is very important to that organism.
So did you have to deal with owls per day to day on the daily? Did anything ever happen? I'm just wondering about the care and maintenance of owls, or was that left to,
Yeah.
I mean, you were a grad student at that point, so.
Yeah, right. No, it's true that despite going into neuroscience, thinking about sort of the concepts and in some ways the theory of it, I actually began more on the computational end than the experimental end. I became an animal handler and an animal caretaker, and in some ways an animal gatherer. So, so we some of the animals used for this research are bred, and so there was a breeder colony that we had, and so we were able to get owls that way. But occasionally the breeders, they get old and they don't breed as much.
Not doing their duty.
Not doing their duty.
Oh, my goodness.
And so this was a case where actually we were quite fortunate for lots of reasons to be in California. And in the California Central Valley, it's a lot of farmlands and there's a lot of barns. And so occasionally my fellow
here.
Yeah, no, it's true. My fellow students and I would occasionally take trips out to the Central Valley and try to convince some of the farm owners to allow us to poke around in their barns looking for owls.
Okay, we'll just leave that there. Moving on from there, I'm not quite sure what happened between Stanford and Philly, but I'm
Seattle.
From your Seattle, Washington.
Yes.
Okay. Anything you'd like to add from there?
Well, it was another in my continuing tour of studying neuroscience in proximity to the Kim family. So as I'm sure you know,
shout out to Dr. Douglas Kim.
Dr. Douglas Kim, but at Stanford it was when Will was there. So your brother Will was in Stanford, and then I moved up to Seattle so I could be close to your brother Doug.
That's sweet of you. And what was your research? Was it continuing with sound localization there as well, or did you shift gears and
shift gears? So up in Seattle, I made a pretty big shift. Well, within the realm of neuroscience, going from sound localization in barn owls to visual decision making in primates. Up in Seattle, they have one of the world's foremost non-human primate research centers. So I went up there to study brains that are much closer in form and function to our own, with the hope of getting a much better understanding of how our brains work in the kind of complex environments that we find ourselves.
This is from an excerpt from your research expertise. You described that many aspects of higher brain function rely on two closely related capabilities, inference and learning. Inference, you say, is the process of drawing conclusions from uncertain data, like forming a percept from noisy sensory information, or predicting the most rewarding future outcome from the recent history of outcomes. So I'm wondering if you could maybe just walk us through an example of how you can scientifically get to that conclusion. And also I'm curious to know if this is based on observable human behavior in a social science setting, or is it purely conclusions coming out of the laboratory, or is it a combination of both?
Good questions. So we'll start with the first. So a good example of the kind of inference and learning process that you were quoting from, actually we can go back to the barn owl. So there's a good analogy here, and one of the reasons why the barn owl is such an interesting system to study. That let's think about the difference between determining where the source of a sound is versus trying to understand where the source of a light is. Start with the light. So when your brain needs to figure out where something is in the environment, there's actually a fairly straightforward process by which it can do that. So you open your eyes. Hopefully it's not too early for you this morning, and you've got your eyes open, and you can look around the room. And if there's some object in the room, that essentially the light from the object takes a straight line to your retina, to the receptors, layer of receptors in your eye, and the place on your retina where that information hits is transmitted directly to your brain, basically by a grid, where the grid maintains the spatial representation of your retina. And so, in other words, there's a fairly direct representation of spatial location for vision going from the object itself to your retina, to your brain. And we would call that a topographic representation, or a map that's projected in a point-to-point fashion, right? So that each point on the retina represents a particular location in space, which is represented in the brain. Of course, there's complications, like you can move your head around and you can move your eyes relative to your head, but that sort of first-order representation sort of gives you a sense that the problem that the brain has to solve for vision actually is fairly straightforward.
It's pretty hardwired.
It's pretty hardwired, or at least the framework for it is. And now let's contrast that for hearing. So as I said before, the way that you know where the source of a sound is isn't based on any kind of point-to-point representation. You don't have this direct representation of space out at the periphery. Your ear doesn't have a map of space. In fact, you're just getting a series of sounds, of acoustic cues, really just vibrations in the air that cause your eardrum to vibrate, which causes signals to go in the brain. And then your brain has to do these very elaborate computations that, as I mentioned before, involve comparing the timing of the cues and the amplitude of the sounds arriving at the two ears. And only after you do those computations can you start to get a sense of where the sound came from. And so that's a very specific example of what I mean when I say perceptual inference, that you have to infer from these indirect cues and these computations where the sound came from. That was a very long answer to the first part of your question. And then the next part of your question is sort of how can we study this in the lab? I believe you're asking whether it's only something that we can sort of find out in the lab, or is there are there examples of this in social settings and in other settings that people can look at? And the answer is that I think that these kinds of problems are everywhere, and I'm certainly not the first to notice this among the very first researchers in.
I thought I had a huge scoop.
A huge scoop that. Maybe so. Turns out that among the very earliest researchers in perception and how the brain works included a sort of a titan in the field named Helmholtz, who was among the first to describe perception itself as an inference process, the idea that anything that we perceive in the world is not based on a direct representation of that thing in the world in our brain, but rather our sensory modalities, our eyes, our ears, our taste, our touch, and our smell give our brains some evidence and some information, but somehow our brain has to make sense of that information, draw conclusions from it, that is, make inferences about what it is out in the world that produced it. And so I think that inference in general is relevant to any situation in which you are sentient and are taking in information that needs to be interpreted in terms of its meaning for the environment that you're in.
Well, thank you. Let me go forward a little bit here. I have yet another quote of yours. This builds upon that one. This is a little excerpt from a synopsis of a 3-year, quote-unquote, brain grant from the National Science Foundation that you and your colleague, Dr. Cable?
Joe Cable. We can call him Cable, but we should probably call him Cable.
Okay, Dr. Cable in the psychology department. And the quote is, "The work is based on a novel hypothesis that, in an unpredictable world, people making decisions face an inherent trade-off. Higher certainty leads to more precise and accurate choices when the world is stable, but an inability to adjust to change. Whereas less certainty can lead to greater adaptability, but also more variable and imprecise decisions." In layman's terms, could you tell us a little bit about this effort?
Yeah, and it relates to these ideas of inference. So one of the well-known and sort of long-standing principles for inference in general is a really simple one that you as an engineer will appreciate, which is signal averaging. When you get noisy signals, that one of the best things you can do is average them. And by averaging them, you tend to, under the right conditions, you tend to boost signal and reduce noise, right? You know, the idea is that on a foggy day, sometimes you have to take a longer look because it takes a little longer to process the information, and really what your brain is doing with that longer look is signal averaging. And it turns out that signal averaging is something that your brain is really, really good at. Even when you don't think you're doing it, you're doing it. That it's been known for a long time that even the simplest perceptual tasks, so tell me whether you see a green light or a red light, or something as simple as that even though it feels instantaneous, it actually takes a measurable amount of time. And it's been known for a long time that time that your brain takes to do it involves signal averaging. And so you're sort of taking a little extra time in order to process information a little bit longer so that you can do a little bit better at perceiving what's out there. So given all that signal averaging that's going on, this work with Dr. Cable sort of asks what is a very obvious question, I think, as befits a lot of scientific inquiry. You sort of want to ask the simplest and most basic questions, which is that if your brain is spending all this time sort of taking time to signal average, then how does it deal with the fact that the world is changing all the time? That, again, as an engineer, you'll appreciate that signal averaging is a really good thing to do if you think that the world is going to stay the same and that the thing that you're averaging is going to stay the same while you're doing it. But what happens if the world changes? What happens if for whatever reason the amount of time it takes you to figure out that the light is green, that it changed yellow?
Right, the novelty.
A novelty. And so the whole idea behind this study is how do you deal with this? It's really a conundrum. It's like a chicken and an egg problem. That if you're using averaging to figure out what's out there, and what's out there changes all the time, then how do you know when it changes, and how do you know what's out there?
So you're midway through this.
We're a little bit more than midway through it. Yeah, in fact,
how's it going?
It's going. It's the kind of stressful time. In fact, the way these things work, understandably, is we have to give a progress report every year.
Sure.
And I've been getting a series of more and more urgent messages saying that our final progress report going into our final year is due very soon. And so the progress of this study is very much on our mind. I feel like we've definitely made progress. So one of the really interesting findings that we're still very much in the middle of trying to sort out is that it turns out that people, and this is one of the studies where we've been focusing on people specifically, and we've had people doing various tasks that involve doing signal averaging in tasks that are changing all the time, and asking to what extent are people able to deal with these changing environments. That not surprisingly, people are very different. That some people are very good in at these tasks, and some people maybe don't perform them as well. Although one of the points that we've really been focusing on is that it looks like, at least under the kinds of tasks that we study, that it's really not as simple as some people are good and some people aren't, but rather, maybe not surprisingly to anyone that has their eyes open in the world, that different people just have different assumptions, and their performance differs based on those different assumptions. And in this particular case, the different assumptions can be explained at least a little bit along a fairly intuitive distinction, which is some people act as if they think that the world is very much stable and seem very surprised when something changes, versus some people think that the world is changing all the time and almost seem surprised that when they sense that there's some pattern of stability. Yeah. And based on those assumptions, we think that that can account for a lot of differences. And so we're trying not to think of differences in the ability to make the kind of inferences that we were talking about before in terms of just sort of better or worse full stop, but rather in terms of just different sets of assumptions. And so the obvious next sets of questions that we're interested in asking is, where do those assumptions come from? And how might we be able to get people to learn different assumptions under different conditions that might be better suited for the tasks that they are embarking on?
Well, I'm very glad to talk to you, because I thought I would talk to you to get to the neural level of change. And these are my podcast is about conversations on change, and so I'm looking more at talking to you is getting more to the root of it. So it's pretty interesting.
I should say that certainly one of the things that has gotten us excited about this line of research is that it seems to have these links to, well outside the lab, that certainly there's an appeal to thinking about how it is that we as humans make decisions and deal with the environment that's changing all the time, and we think that we're able to study it a little bit. Before we continue, I feel like it's important to add that very important caveat that we still don't know whether the tasks, the sort of very simple tasks that we can study and control in the lab, really are telling us about the same processes that go on in more complicated real-world settings. But that said, it's a useful and important first step.
Well, I remember when I was in university, I just dabbled a little bit in neuroscience, and because I was too busy with my engineering curriculum. But anyway, they would always draw a rectangle. The professor would draw a rectangle on the chalkboard. On the chalkboard, I don't know if you use chalkboards anymore, but chalkboard.
Yeah, not as much anymore.
And they'd write higher learning on there, arrow in, arrow out, and then big old question mark in there, it's a black box. So it sounds like there's been more detail added to this over the decades. So that's encouraging to me.
There is, yeah. It's slightly, we understand it's slightly more than just a box on a chalkboard, although, maybe for parts of it, that actually may be an appropriate level of description of our understanding.
Anyway, well, thank you for that. And Dr. Cable and Dr. Gold say at the end of their page, their website, that the two Penn researchers have placed a priority on increasing participation of underrepresented groups in this kind of integrative research via summer research experiences for high school and undergraduate students. So the podcast is, well, don't tell the kids. It's a little bit of reverse psychology. I had a psychologist actress asked me recently, well, why do you call it this if you want the kids to listen? I'm like, well, that's encouraging to me to see this trying to increase participation for underrepresented groups. Do you want to speak to that a little bit? And I'm just thinking about the next generation of scientists and encouraging them and getting them into the life of science and academia.
Yeah, absolutely. I'm glad you asked about it, because it's something we're definitely very proud of. And here it is our federal government that deserves an enormous amount of credit. And so the funding, which is why I'm trying to emphasize them, because there are definitely cases where it's merited and it's so lost in the conversation too many times. But so funding for this project comes from the National Science Foundation, one of the two main entities that fund this kind of work from the federal government, the other being the National Institutes of Health. The basic distinction between the two is that the National Institute of Health, or NIH, really take a focus on more disease and clinically related questions. Right. And the National Science Foundation has been, really by mandate, separating out the more basic science questions. And so this project, as we've talked about a little bit, is really about basic questions about how the brain works and solves these problems. And both NIH and NSF, but in this case through NSF, have really done, I think, a wonderful job of focusing researchers on these questions of these broader issues of societal impact and bringing in groups into science, into participating in science that traditionally have been underrepresented. That it can cover lots and lots of different groups, but groups from different ethnic and socioeconomic origins, and just in general, people who have not been exposed to science from early in their lives tend, not surprisingly, to be people who don't think about science as a career or really or in any way. And so we, trying to do our little part in that, have also been trying to bring in groups and people to be involved in our research, particularly over the summer, that wouldn't have otherwise done that. And it's something that Penn is also been very active in, and so we've been very fortunate to have a number of students, mostly at the undergraduate level, but in some cases high schoolers actually come in and spend a summer and just sort of learn what it is to do science. And in my experience, they have been absolutely fantastic. There's nothing like the wonderment and awe that you can see in the face of someone who is seeing what scientific discovery is like for the first time. Right. And there's something absolutely inspiring about that, and it sort of is a reminder that it's a field that we are very privileged to be a part of, and that we never want to lose that sense. And so bringing in people that it's just that comes across in its purest form, is hopefully a great learning experience for them, but I guess what I'm saying is it's also just a great thing for us as well to sort of maintain the enthusiasm and the spirit of this enterprise. And working in a laboratory, again, there's just sort of this unique opportunity that it's a very special kind of teaching where it's really more mentoring and oversight, and it's providing an opportunity for these students to make discoveries on their own, right? It's one thing to stand in front of a classroom and feel like you're providing instruction and useful information. It's a whole other thing entirely to bring someone in, set them up to be able to work independently and watch them make discoveries on their own. That's the kind of thing that I think really sticks with people, and hopefully in the long run is going to inspire a lot more people to take up this calling.
Yes. Well, it sounds almost apprenticeship aspect to it for the training of just the basic lab protocol and procedure and things like that. And then...
Yeah, no, very much so. And, we already went over sort of a very striking example of how specialized the skill set and knowledge needs to be for any given set of scientific questions. As I mentioned before, I took neuroscience as an undergraduate, and I, learned in the classroom, felt pretty good about my general knowledge of neuroscience beyond a square drawn on a chalkboard. And then I show up to my PhD, and I need to learn how to climb around barns and find some owls. And that's a pretty extreme example, but I think it makes the point that once you decide what are the scientific questions that you want to ask, and you feel like you have a good justification for them, then there's a whole set of skills that you need to learn that you probably didn't anticipate in order to be able to become really good at it. And so that, that's certainly a lesson for any young people thinking about careers in the future, that it sort of speaks to the cliched but very true point that you find the things that you're passionate about and you enjoy and you like to think about. then all the details will follow. Then you have to, from there you've got to figure out what it is that you have to do to get from here to there. And if you're not excited by that path, then that's probably not the field for you, because there's just all sorts of directions it's going to go that are going to be unexpected. You've got to be jazzed up the whole time to tackle these challenges. And so I guess this is a bit of a meander from the original point, that the lab really is like an apprenticeship, and you find, you come into this environment and you can start to learn what are the different directions that you can go, and what are the skills you need to learn, and how do you go about learning them.
One of my guests a while back talked about a book called Grit. And
I assume that it was prominently mentioned, the book Grit, written by University of Pennsylvania faculty Angela Duckworth.
Yes, that's right. I listened to her TED Talk.
All roads come back to Penn.
No. They come back to McLean.
And McLean, right.
There must be something to be said for perseverance and grit, especially in this field of scientific pursuit.
No, absolutely. I'm sure that it's true of any field. In podcasting, right? It's that there's some part of it that at this point that you're feeling comfortable with, but you're constantly learning and constantly pushing, and to get really good at it, you have to sort of be truly dedicated. And that's absolutely true in science. That we talk all the time up here with my colleague Joe Cable and other collaborators, and when we're trying to identify the right people to work on projects, that even from the description that you read from our project, right, we have a pretty good idea of what we want to do. And, that's how we convinced the National Science Foundation to give us a grant to study this. Even if that plan is, let's be wildly optimistic and say that it was 90% correct of what we're going to end up doing, it's that last 10% that ends up mattering the most. And it's that last 10% that we rely on the people doing it to figure out. Like, if there wasn't uncertainty in the scientific questions, it wouldn't be worth doing. But because there's uncertainty, it means that we don't know what's going to happen next. We don't know what result we're going to get and what that's going to mean, and how we're going to have to change the way we're thinking about a problem, or maybe redesign the task or redesign the experiment. And the ability to, I think grit captures this sort of nuanced ability to deal with it when things aren't the way that you expected. And it's so important for the success of science and anything else to be able to deal effectively with those situations.
That's about all the time we have for right now. I wanted to thank you again, Josh.
Well, thank you so much for having me. It was a real pleasure to join you today.
And thank you all for listening. My guest has been, once again, Dr. Joshua Gold, and I'm Janet Lee. So please stay tuned for more episodes of Well, Don't Tell the Kids.